Hello, everyone, and welcome to Structuring Data for Machine Learning and AI Success in Biotech. Thanks so much for joining. My name is Bernie Lee. I'm a product manager here at LabKey Software for our biologics LIMS, and I will beg your forgiveness in advance. I'm almost totally over being sick, but I occasionally have to pause for a moment and cough. So bear with me. Today, my goal is to equip you with the knowledge to prepare and perform data structuring processes for effective machine learning application in biotech, emphasizing the critical role of data quality and organization. Really quick, though, LabKey has been helping academic, government, pharma, biotech institutions manage scientific data for over 20 years. We aim for a genuine partnership to ensure that you achieve your goals and that we can learn from you. And as you might have guessed, many of our partners have built or build data science products that interact with data in our system. So we get to be involved with a lot of this stuff firsthand. So let's start with why all of this matters. You're all on endeavors that are sophisticated, difficult, specialized, and important. They are often very expensive and time-consuming. And ultimate success is relatively rare. There are many hurdles along the way, scientific, operational, and with data, and each area must not be excessively rate limiting, but also each is made up of lots of individually contributing people and components, making it kind of complicated to streamline. So, of course, ideally, you could simply, type, I want an antibody design for transthyretin fibrils in the heart. And your special AI search engine will spit out the sequence for you to go and synthesize and confirm. It'll be an amazing day. The reality is closer to, maybe we can streamline certain parts of the process, increase our efficiency for some, and overall reduce risk. For the pragmatic among you, you'll recognize this as being desirable. This is an admirable goal that could accelerate operations and learning. So that's really what primarily we want to aim for. Before we jump into some of the key challenges and best practices for pursuing this kind of project, I just want to mention a handful of examples from around the industry. Some of these might be quite familiar to you, and others maybe not. I selected just a few to share in the hopes that they'll provide just a little bit of context for the rest of this talk. So a few that I've selected are classifying and predicting protein structures and performing molecular design using things like artificial neural networks, predicting the location of protein encoding genes from sequence databases and the DNA sequence itself, microarray expression pattern identification through classification and irrelevant data reduction, predicting binding sites from biological component data, and things like phylogenetic tree reconstruction to include genomic comparison. If you go look at various publications and just run a random search online, you're going to find an incredible number and a range of these things, and each involves potentially very different data, but the same fundamental principles drive success. So, what do all of these successful data science projects share that make them so? What does it mean to be successful in an endeavor that involves machine learning AI or another data science product that might be applied in biotech? And I want to keep this simple. Success means the scientists can spend most of their time using their specialized domain knowledge and very little of it on transforming data around or other, data-related menial tasks. And then, perhaps in addition to that, success means having clear metrics that demonstrate time savings or added superpowers from some modeling product. It's the value of having the data science product in place. So there's a role for data science in driving down the cost of many scientific endeavors by reducing or replacing experiments and reducing clock time. But it is critical in most cases to keep the true goal in mind and not, as I certainly and many others are so inclined, to pursue the really cool project kind of for its own sake. So why is this hard? I know it seems like everyone is doing this, or at least everyone wants to do this. So it must be easy, right? But there are many, many difficulties. And even if you have succeeded to some degree, there are probably ways to make it easier the next time. So architecturally, unlike more common rule-based programming, machine learning, for example, consists of essentially two parts that make up the final executable algorithm. There's the machine learning algorithm itself, and there's the data to learn from that you train it on. But raw data are not typically ready to be used directly in machine learning models. So data preparation is kind of the heart of machine learning. And it is this preparation and the scientists with their processes and that produce the actual data that's really worthy of our focus. So you'll hear this all over the place, but it's true. The preparation might be more important than the algorithm itself, because of course there are lots of added benefits that come with the preparation. So you need to explore and understand your data before you try to jump into something like machine learning. So starting from the highest level here, for data to be useful beyond one scientist's immediate needs, regardless of whether machine learning is the ultimate destination, it really needs to be structured, consistent, and interoperable. So some quick definitions, I suppose. Structured data is anything that conforms to a set of rules and conventions. Really mundane. With a good example being data that can be, say, naturally cast into a tabular form. However, unstructured doesn't mean poorly structured, like having the same info in tables and different headers and naming conventions and things like that. Unstructured can be text without defined patterns, mixed information, or images, which are inherently unstructured. Excuse me. You can, of course, process all of your data in every form on the way to the model, but this structuring matters because data science models can be very performance sensitive. The more processing that you have to do along the way, like more processing you have to do to train and run the model, the more challenging it will be ultimately to find success. Going down, I don't have to tell you what consistency means, but if everyone is doing things differently, or if the same people introduce variation into their data, making use of it after the fact can be extremely difficult. And interoperability is the ability of software to exchange and make use of information. Okay, very, very simple, big word, simple concept. I typically think of APIs, direct database access, but of course, not everything's in a relational database. So scientists will always find ways to accomplish what they need with their data. I assume most of you are or were scientists. And so you know this. We have to have high ingenuity to be successful. But in this context, it often means falling back on the tools we know, spreadsheet operations, when alternatives are too difficult. And this can introduce poor structuring. And it implies that whatever data management tools are employed must therefore actually improve cycle time for scientists, or at least not slow them down while providing the benefit elsewhere, like as part of large-scale analyses, machine learning, AI, and other kinds of data science applications. So different teams, different projects, and people will structure differently what's essentially the same data, unfortunately. The example being, different groups might use different templates for the same thing. And if they don't have cause to communicate and align, this will result in different formats between different projects, introducing inconsistencies. And then it's important to explore where the data will end up and in what form. That's kind of the interoperability part. Is it the same between teams? Do scientists, say, drop result files on their own computers or into their own shared folder space? Or is it imported into a database somewhere and in a form that's accessible, recognizable, and therefore useful to others? No, it can introduce interoperability issues. Okay, volume, diversity, and complexity of data. So let's talk about data quantity. You want the amount of data necessary to solve the problem at hand. Is more better? If you need to detect small, meaningful differences, you will certainly want to pursue the difficult aim of getting sufficient quantity of quality data up to some point of diminishing returns. But those diminishing returns are real. So, for example, everyone's favorite AI chatbot was trained using a text database from the internet, and is thought to have trained on something like 300 billion words or 570 gigabytes, which will be how many words I speak in the next 25 minutes. Just kidding. Maybe. Would a lot more have been better? It's a reasonable debate. I'm sure they had. On the other hand, if you're preparing data with a particular task in mind, as opposed to a generalized language thing, having a huge amount of imperfect data can demand a huge amount of work. It's very often better to reduce data, to start small, reduce the complexity of your data, and perhaps more importantly, tailor your data gathering mechanisms toward the desired ends. All that said, you definitely want to collect all the data that's possible. I want to argue, however, that volume for most biotherapeutic development and other biotech endeavors is actually not as big of an issue as an outsider might expect. We're used to hearing about big data problems like Amazon generating kind of a deluge of data on a sub-second basis from all their user interactions, and then having to tease those things apart, to find various meanings within. Biotech doesn't often do this kind of thing. We mostly have discrete runs of data generated by rate-limited instruments. And the way that we increase data quantities is with things like high-throughput technologies. And there's diversity. Do you really collect 1,000 different data types? Probably not. Most often, real variation in data types are artificially expanded by different people interacting in different ways with similar data. And so it kind of masquerades as diversity. You might even call it inconsistency. As an example here, you might have multiple people running extremely similar assets, and they may name it something a little bit different and name the data attributes differently. But really, there's no difference, or just a column or two different. And failure to get a process in place to check similarity and adjust with future use in mind leads to an artificial inflation of data diversity and probably complexity. And this in turn adds hurdles to large-scale analyses. And then there's complexity. So some types of data do not lend themselves well to structuring. They require heavy processing, transformation, or conversion to be structured into, and conversion to be structured and integrated. So as I mentioned before, there are things like images, there are spectra, chromatograms, transactional data, like sensors for continuous monitoring of bioreactors, things like that. Now, all these data types you can convert into something that is more structured and supports the end goal, but all of those things have trade-offs. So, for example, a well-encoded and modest pixel count JPEG file image requires, in the teens, 13 kilobytes of data to store it. Whereas a float 32 tensor, which is great for machine learning because it's highly performant, uses something like 798 kilobytes of memory. So it's like a 6,100-ish% increase. And so, you can make changes to these things, but you have to think about all of the trade-offs. So let's say you've largely overcome some or all of those challenges. In order for some model to be useful, many of your data types need to be integrated to produce the contextual landscape that can actually answer your scientific questions. So very often, scientists are manually combining results with sample data and experiment conditions and upstream data about sequences or clones or other sources, and using the results to make certain decisions and keep records. A more concrete example, if you're tracking machinery sensor readings on bioreactors to enable predictive maintenance, most likely you're generating logs of transactional data, which is like events that snapshot specific moments in time as you go. But you can add such qualities as the equipment model, the batch, its location, to look for dependencies between equipment behavior and its attributes. And for something like a bioreactor, you're also going to be drawing samples out with information about those samples, which need to be associated with assays that characterize the material that you pulled out. And these are all separate systems. You know, separate systems to collect that high frequency sensor data, pH, gases, scale weights, things like that, which are relevant context for the samples that you draw out and the ultimate experiment success. And all of this you have to integrate to make good determinations on cell culture health and bioreactor operation. And this means, among other things, you need to rectify and align identifiers and timestamps and everything else, and then ideally store it in such a way to support programmatic accessibility and usability. And this is no small feat. Okay, the last key challenge that I want to touch on is institutional, structural, and possibly precludes overcoming all of the other challenges. And that is institutional support and structure required to organize, coordinate, and implement changes needed to successfully use data science products at all. Many of the aforementioned challenges are simply not problems data scientists, are not problems that scientists and perhaps IT professionals and software development teams are actually prepared for. Some are, but I wouldn't say that's the rule. That makes higher order data work for an arbitrary chosen set of scientists beyond a reasonable scope of responsibilities for many, especially since the required changes impact their and other people's processes and daily operations. And so organizing your institution to support these efforts can be a precedent required for success. So as part of that, data science and data engineering groups with data management tools are really valuable to have for a biotech. Okay, more on that a bit later. So we've reviewed many of the key challenges faced by those who wish to implement data science products in biotech. Now it's time to start solving the problem a little bit. So this begins with a clear problem formulation, which is sort of the way everything is, right? But it will provide guidance on what data to capture and how to process it, what additional work will be needed for the model. It will begin with the people that a data science product might serve. As often as not, your scientists are going to come to you with those problems. But if they don't, begin with the people who have the domain expertise. It is critical to incorporate domain knowledge into the data structuring, processing, and conclusions. It's their knowledge that will help you select relevant data features, understand and neutralize potential biases in data collection, and ultimately judge utility at all. So I found a great story to make the point. It's a well-known story, but I think it's a good one. So there was a healthcare project aimed at cutting costs in the treatment of patients with pneumonia. And they employed machine learning to automatically sort through patient records to decide who has the lowest risk of death and should just go home and take their antibiotics, and who's at high risk of death and other complications from pneumonia and should be in the hospital, in the ICU. The team used historical data from clinics, and the algorithm was accurate. But there was an important exception. One of the most dangerous conditions that may accompany pneumonia is asthma. And doctors always send asthmatics to intensive care, which results in minimal death rates for these patients, which is good, right? So there was an absence of asthmatic death cases in the data, which made the algorithm assume that asthma isn't actually dangerous during pneumonia. And in all cases, the machine recommended sending asthmatics home, despite having the highest risk of pneumonia complications. Okay, so not all data scientists know that asthma can cause pneumonia complications. And of course, in your context, there will be similar domain expertise. But a quick conversation with a doctor or the scientific team that is involved with some of these things would tell you such things. So if you and the model have incomplete information, despite even terabytes of relevant data, the machine will be nearly useless or harmful. Excuse me. So there's now commonly used simile that being a great data scientist is like being a great chef. To create the desired meal, you have to possess great familiarity with all of the potential ingredients so that you can understand how to prepare and combine them in a complementary fashion to produce a balanced and memorable memorable meal, an extremely high-priced memorable meal. So with clarity around the problem you're trying to solve, you can begin to lay the groundwork for that meal, for that great machine learning model. And you need to consider the whole data lifecycle. That is, how it is typically captured, processed, analyzed, and stored. If you can clearly identify what will happen at each step, at each stage, then you can select the right tools, the right places for these operations to happen, and so that people don't fall back on extemporaneous and variable spreadsheet use. I want to briefly emphasize analysis as part of this data lifecycle, because this is how fundamental scientific questions are answered, and where most of the data manipulation occurs to achieve it. So it's towards these aims that data is transformed from its original state, is annotated, integrated, calculations are performed, visualizations are generated, and it is very often that these questions lead to good data science projects. Okay. We are going to dive into some of the nuts and bolts here. I don't actually have time for an exhaustive or comprehensive discussion on a lot of these, so I'm going to try to do a quick but high-value sampling here. So structuring and standardizing your data. There are a variety of practices that can help you stay sane, as well as make your data science endeavors much easier. They center around choices that your organization can easily make with a little forethought and coordination. So as some of my previous examples have suggested, adopting a common data model across projects, across teams, or however you organize yourselves, can be the foundation for consistent structuring. Common here implies shared, and it implies that those using it have influence over its formation, okay? Not imposed on them. Within the framework that your data types are appropriate and consistent, it might be a silly example, but like a numeric measurement could be stored as a string or as a number. Or take the money example that I have up on the slide here. These are three legitimate ways to write the same thing: $4.03, $4.03, $4.03. But make a choice together and stick with it. Similarly, silly example on consistent naming is that you should decide if you're going to call it T, temp, temperature, degrees Celsius, or if you're feeling really nerdy, enthalpy. I will say on this one that most data management tools will actually store it one way, but allow you to call it a variety of things, and alias that field. But this is actually kind of a case in point, though. The data management software is enforcing a standard within itself, even if it accommodates your variability on input. Okay, you want unique IDs for entities of interest. So this is fundamentally how you and your data scientists make distinctions. If you can't distinguish between unique entities, there is no analysis that can be done beyond the immediate data, and certainly nothing a machine learning model is going to be able to do. Avoid free text. There are upwards of 170,000 English words in use, producing an effectively infinite combination of free text entries possible. So find reasonable ways to constrain choices for information entry, even if the list is long. Having a standard known set of choices makes the data usable. And if you don't, you first have a natural language processing problem or a text annealing problem, and then maybe it's useful. Okay, validation rules. This is a serious data quality concern and actually a rather deep topic. But validation rules ensure that things like ranges of data are appropriate, bad values are kept out, and outliers are excluded or rectified. A few examples to paint the picture. What is an appropriate age range for a human? The oldest human ever died at 122 and a half years. So hopefully we could agree that the age range is something like 0 to 125 years. That means you should not accept ages that are in the 4 digits, that are negative. Similarly, there are only 12 months a year. We don't operate in hexadecimal. I'm not aware of temperatures below absolute zero. Food is either raw or cooked. I think you get the picture. There are also relevant custom validation rules. These are things like dependency on some other column of data or set of columns of data, where the other columns dictate what's valid for this one. And so these are rules that you have to think through for all of your data. Okay. As I said before, integration of your data creates the landscape from which scientific and practical questions can be answered. And this requires alignment of different data types, which, by the way, becomes almost impossible if you don't have unique IDs for entities, as I said in the last grouping. It bears repeating here that converting all of your data to the right and consistent type is really important. You can imagine, to use the same silly example I did before, that two types of data that you capture for temperature, but one of them is numeric with one name, and one of them is text string with another name. Now, any data science model that cares about temperature has to somehow do that reconciliation on the fly, which is not good. Okay, we're going to talk briefly about key alignment. Pardon the somewhat technical term here, but it's actually a really important concept, which I'm going to try to make clear as quickly as I can. So ensuring consistent key values is crucial for accurate analysis and avoiding errors. Typically, multiple rows from multiple data sets often are pulled from different sources, but they all relate to the same entity or observation. So one or more key fields are used to tag all of the data with each entity. And then a common challenge is aligning those key alignment, where the key values associated with each one can fail to match consistently across all of the different data sets. For example, different data types are used, or string-based keys use is inconsistent formats. They have leading zeros or trailing spaces, different capitalization or punctuation, and failing to fix these issues can lead to a lack of alignment, can lead to inaccurate analysis due to the introduction of fictitious observations or the loss of data associated with true observations. And of course, if these things are a problem for local analysis, it's totally catastrophic for machine learning. Okay, and lastly, you will have missing data. At best, when you start integrating and combining data from many experiments, you'll find that some assays weren't run, probably for a good reason, that some sample information was not captured, again, probably for a good reason, and that these and similar gaps are much more glaring for data science than they actually were for the original experiments. And it turns out the best practice for machine learning is to fill in those values for the algorithm training that are appropriate. That turns out to be better than having no data there at all. Okay. The importance of metadata. The other dimensions of data I refer to as metadata. They provide the context and conditions for key measures. Metadata is important because you don't just want to, for example, know the optical density of some sample. You want to know how samples compare to each other, and whether your conditions allow you to make that comparison. You want to know how something upstream of your measure affects your materials. These simple questions require adequate contextual information. And as you move into data science products like machine learning and artificial intelligence, and other large-scale analyses, the richness and accuracy of this metadata becomes paramount since it shapes the model itself. I'll use an example to explain. You have an amino acid sequence and calculated physical properties that you need or that you use, and you want to be able to predict what purification method or methods to use, which ones are going to be best. By testing under various conditions, like different resins, different pHs, you can learn what the yield and purity are for the molecules that you have. And then if you can model it right, you can extrapolate from similarities between the training sequences and other properties what a new sequence most likely needs. That's the goal anyway. You obviously need the annotated sequences that you start with and the pH and resin information, but you also need to capture things like starting quantities, so you know what your yield means, and what cell line was used to make your protein, and the reagent information, et cetera, et cetera. If you fail to capture that metadata and something important varies, like the cell line or whatever, it can just categorically change the downstream measures, and the model will simply be incorrect. So no matter how much data you have and how much expertise you have to wield, it won't compensate for that incomplete context. Okay. Next up is what form you store your data in for the purpose of data science products. So we already talked about interoperability, the need to have the need to be able to programmatically access your data in a structured way, but there's not a universal format that magically facilitates machine learning. As you've inferred, it depends on the problem you want to solve, the kind of data you have, and this inevitably leads to transformation requirements by data scientists, but not all transformations are created equal. Ultimately, there's some forms of data which are more optimal for machine learning, but that doesn't necessarily have to be the primary way they're stored. Because it's not universal, what I can maybe help you think about is finding the data, regardless of how it's stored. Whether it's pointers to files and metadata or some relational star. It doesn't need to be stored in such a way. It does need to be stored in such a way that there's a query mechanism. You have to be able to ask a system for certain data in a certain form. If you can't do that, it's all manual gathering and it's a nightmare, especially at scale. And I will also add that your life will be a lot easier if that stored data is somewhere that interacts nicely with Python. The Python language just has so many built-in mechanisms to help with many operations necessary for machine learning modeling. And this means that if you can use some data management tool that offers a Python query API, for example, you really should. Okay, and no talk would be complete without at least one mention of automation. I'm not talking about robots to improve your throughput here. I'm talking about automating components of the data lifecycle to collect more data that's cleaner and more reliable. Because if you are training a model on publicly available data, like some nucleotide or amino acid sequences, or you're building everyone's favorite AI chatbot, there are great resources available. However, the cost of collecting reliable lab data for yourself is much more expensive. So the cleanest data is the stuff unchanged by a human. If you can start your automation process with the raw data, do it and be happy. If you're reliant on people to enter information, you are going to be somewhat rate limited and you might have accuracy and consistency issues. For example, when a scientist has a spreadsheet in place, you have to identify what's in there, what's a calculation, what's copy and pasted from somewhere else, what is sourced from somewhere else, and that can be very difficult. The automation allows you to process and analyze the data consistently and ultimately store it exactly where you and everyone else expects. This will make everyone far more efficient, less frustrated when the older data needs to be found and used for something else. So consider what you can automate. Consider what impact that might have on your scientists. Consider what impact it will have on your institution as a whole. And this brings me back around to that institutional support. So scientists will understandably find the lowest entropy approach to their own data management needs. And any imposed data collection, processing, and storage tasks may be tedious, burdensome, even overwhelm them when added to all other responsibilities. If people constantly and manually make records, the chances are they will consider these tasks to be another bureaucratic whim, and they're going to let it slide. So to return to our success criteria, have a team whose goal is to ensure scientists are spending most of their time using their specialized domain knowledge and not pushing data around for themselves or others. That might mean hiring data scientists, data architects, data engineers, and deliver value to scientists and staff effectively, in part by having those clear metrics demonstrating the time savings from some data products that are enabled by your efforts. Use data management tools intended to govern the whole data lifecycle. You do not have to do this all by yourself. And work with leadership at your institution to create a data-driven culture and prevent the kind of data fragmentation that otherwise is inevitable. This is precisely what we aim to do at LabKey in our partnerships with clients. We help you prepare and manage your data so that whatever machine learning or other data science method you want to explore, you're as ready as you can be. And with that quick shameless plug out of the way, I would like to thank you for spending a little time with me today. And I'd be really happy to take any questions you have. Please use the Zoom Q&A feature. And of course, if there's follow-on conversation that anyone would like to have, we'd love to hear from you. Thanks so much. Can you have these slides? I'd be happy to share the slides actually. Um, yes. So if you signed up for this, which obviously you did, you will get access to the recording. And you know, for the person or people that are interested in the slides themselves, I'd actually like to ask you to send me an email. I think you all should have my email through this program, and I'll get you a version of it. I'd be happy to do that. And then yes, it usually takes us a couple days to turn the recording around, and you should get a follow-up message that a recording is available. And then love to have you review that, share that, and come back to us with any questions. Any other questions? Happy to field them now. Oh, there we go. Okay. Let's see. How does LabKey manage different types of data collected from different analytics to combine, especially when there's missing data, let's say per sample ID from different assays? Yeah, so there are a variety of ways to align data. In LabKey, our go-to is to align on the sample itself. And we have all kinds of tools in place to help you manage samples, generate those unique IDs, and use them in each of the variety of places. And so what ultimately happens is when you're doing that sample management with us, and you run those samples through any assay, we automatically on import connect those things up. So you can go and look at one sample and see all of the different things that have been run on it, or a group of samples, and get the same kind of thing. So yeah, behind the scenes, that's, we use some sample ID alignment magic for you, and that's something that we'd be happy to show you if you're interested in. Okay, we got another one. Thank you. What's the best way to attach metadata to files using an associated JSON file, like storing them in some bucket storage blog in AWS or Google Cloud Platform, for example? Also to be recognized by tag catalogs for data pipelines. I would love a little bit more context for this. So with apologies, what I'm going to request is maybe an email or a conversation follow-up on this one, so that I can give you a coherent answer, just to make sure I understand exactly what you're really asking. Any other questions? Oh, we do have one there. Okay. Can you talk a little bit about data governance aspects in biotech in general and how it differs compared to other verticals? Sure. This is its own webinar topic, honestly. Yeah. Okay. And data governance means different things to different people. So I'll try to answer it the way that I understand it, and we can iterate in the future if it's relevant. So, data governance aspects in biotech. So, typically in biotech, there is a desire to fiercely protect your IP, which is your data, and perhaps some of your materials, but fundamentally, it's your data. And so, you want predictable systems in place with controlled access to these things, but you want the people that are supposed to have access to them to have great power over them, as well as auditing for what's happening to that data. So, this is one of the fundamental problems with, baseline spreadsheet use, which is that essentially only the individual involved that's using them has control, and it's ungoverned. It might be structured in the technical term that it's in a predictable format. Essentially, it conforms to some rules, but fundamentally that data is ungoverned. And so most data management systems, certainly ours included, have all kinds of data governance rules. Where you can put data, what it means, how it connects, who can do it, how it's audited, all of those actions. And in general, I find that in biotech and pharma, that is where it is in the highest demand for commercial reasons, frankly, as well as security reasons. That's of course also true in things like healthcare, where all of that data absolutely has to be very, very, very tightly managed. How it compares to other verticals. I mean, I assume you're talking about other aspects of the business, possibly, and typically those other parts of the business are not the IP. They are not fundamentally what is driving potential revenue and potential, say FDA and EMA approvals. And so it matters differently. It matters less. The way that the teams coordinate and operate is just a little bit different. I'm afraid I'm starting to ramble a little bit, so maybe we could iterate on this question a little bit more, and I could more specifically address it. Thanks for asking it. And I got one more that came in here. We have different legacy data types in various formats, Word, Excel, images. Can we get this data into a central database system in a structured data form? And is it possible to fetch this data on search and visualization? Yes. Now, I won't say that zero cleanup will be required. Almost certainly there is. But I'll tell you two things. One is that when we get new clients, I think this is true of really any data management system. When you start working with someone, you have two approaches you can take. You can start by trying to clean up what you have and fit it and start collecting going forward. Or what we typically recommend is let's get the system set in place for from now forward, and as essentially a separate problem, figure out how to best shape the existing data and bring it in so that, from as early as possible, you are beginning with structured, governed data, and essentially treating that legacy data as a separate problem. So, Excel can be pretty easily transformed so that it can be imported into data grids and tables. We certainly have a variety of mechanisms for that in LabKey products. Images and other kinds of files that you kind of want in that form for reference, of ways of associating that with samples, with results, with other sorts of things in our system as well. That's native. And then the Word files, that one probably is worthy of a little bit of exploration. I don't know if that's your, essentially your ELN, or whether that's, free text descriptions of some other piece of information. We do help with that. And I think probably most data management systems have some mechanism for extracting that information and making use of it. And then, yes, once it's in a structured format, a data management tool like ours, you can text search, filter, sort over the data, and use that to generate visualizations. A lot of applications, ours included, have some visualization capabilities, as well as very often the ability to create your own with, maybe you're a ggplot2 developer who likes R. A lot of organizations, ours included, allow you to make those sophisticated visualizations through means like that. Okay. Anything else? I'm happy to get these questions later. Doesn't have to be live. So I think all of you have my email, and I want to thank you again for joining me today. We'd love to hear from you if you have anything else to say, and you will certainly hear from us with that recording. So again, thanks so much for your time, and I really hope that you learned something today. Thank you all for coming.